All right, recording is rolling. Today's Wednesday, November 17th. You guys just saw a few videos. There were a couple Paul Hewitts, and there was one with a gyroscope that looked just like this one. So, gonna go through the tail end of these rotational dynamics topics that we've been working on for the last few days. Today, with the angular momentum. That's what's going to explain what you saw with Paul Hewitt and the weights on the turntable, and also this gyroscope. And then tomorrow and the next day, I got a fun project lined up for you guys with O'Neill cylinder. So we'll also review what the physics of that type motion are. All right, so uh, back to paper. Right. So angular momentum. Well, let's go back and look at linear momentum. Linear momentum. You guys remember linear momentum was a vector quantity. We're calling it p, lowercase p, right? And it was mass times velocity. And velocity was also vector quantity, right? Okay, so if you want to see, you remember that this was conserved within the closed system, that whole thing. We were using that fact to solve all kinds of collision problems. Okay? So let's switch over to a rotational case, call this angular momentum. What's something to do with like momentum in a rotational type case? I'm going to designate this capital L. Okay. Now this is going to be a vector quantity also, okay? So like that spinning gyroscope. Okay? And what are the rotational equivalents of, say, mass and velocity? Well, mass in a linear sense is a good place for inertia, represents some amount of inertia. And you guys remember that if something's rotating, it has I, like rotational inertia, for a single point that was mr squared. For a bunch of points like this turntable, be like the sum of mr squared. And you had book values that you could look up. Here, get point out real fast. It was this page 206 in your guys' textbook. Right? What's the rotational inertia of these different objects? You guys remember that? It's like a standard for inertia, but in a rotational sense. And for a solid cylinder, it was like 1/2 mr squared. And then instead of v, we're interested in omega. Like, what's the angular velocity? Like, how fast is it spinning? Right? This is also conserved in a closed system. And we'll take advantage of that to explain, these couple of concepts here. Ice skaters and gyroscopes. Okay, those are the two pretty cool stories that you can explain with this physics concept of conservation of angular momentum. Okay. So let's start with the ice skater example, because you guys saw Paul Hewitt on this turntable. Sketch that up. And let's do before and after. And so there's this turntable. There's the before. Here's going to be the after. Okay. Paul Hewitt was standing here, and he had a couple of masses that he was holding really far out. Exaggerate that a little bit. Got mass. Okay. And he was spinning at some omega, so some number of radians per second, right? Angular velocity. I'll call that omega naught, because you guys definitely saw that change. Okay. And it changed when he pulled these masses in. So here's state 2. Pulls these masses in really close to him. Mass. Okay. And then you saw him speed up spinning. So some kind of omega final. What was that about? Well, I definitely see that his rotational inertia changes. You guys remember rotational inertia? You guys remember those 2 meter sticks that I passed around the other day? It actually looks a lot like that set, doesn't it? You guys remember these 2 meter sticks? And you guys got your hands on these. You guys got to feel these. So this top one, first of all, these have the same mass and the same weight. And at a glance, they might look the same, but the location of the mass is different. So the top one, you can change its angular velocity really easy. Had hardly any inertia at all in the rotational sense. But this bottom was like really hard to change the same motion. Top one, all day. This one, really hard. Right, a lot of rotational inertia. Some of them are squared. That hold in. That's a lot like what this looks like. But you know what's conserved from left to right is angular momentum. So the initial angular momentum and the final angular momentum had to be equal. That's conservation, right, for this closed system, and it was a closed system, right? Okay. So this is going to be the setup, like the framework to explain why is angular velocity change. Now you might wonder, well, hold on, why not use another method like conservation of energy, something like that, right? And it's a similar issue to regular linear momentum when we were solving collision problems. Okay? And here's sort of why. Is that, do you guys think it would take some effort to go from the left picture to the right picture? He has to pull those masses in, maybe apply a force for some changing distance. Force times distance. Do you think he has to do some work on these masses to go from left picture to the right picture? That would like increase the kinetic energy of that system? It would. So if you did like conservation of energy or something, that would like totally the wrong answer. Okay, that's why you gotta do conservation of momentum. Same issue when we were doing like collisions. Right? We had to do momentum conservation. This will solve this all day. So I just gave you guys this formula, I times omega. Remember, this is analogous to m times v. Okay? But I'll do omega naught, right? I naught and omega naught. These are vector quantities. It's a little vector error. And then in the final state, we had some different rotational inertia and some different angular velocity. Now, some of you guys might be able to pick this apart just at this point and say, okay, well, if this product has to equal this product, you have to equate. And the I value decreases from left to right, which it definitely does. Rotational inertia went down. Right? Then do you guys see that omega has to respond by increasing? Right? One goes down, the other goes up to compensate. Right? And if you don't quite see that, then let's throw some numbers in here. I'm just going to make up some crazy numbers. I don't know how accurate these would even be, but just make up some numbers here. So let's call I 50 kilogram meter squared. Now this, I should have asked you guys what the unit would be, but you would have said I is mr squared or some version of that. So there's m kilogram, r meter squared. Okay. And then omega, let's say it was initially spinning at like 10 radians per second, which is actually a really fast rate, but never mind that. So omega. Right, and then in the second case, let's say it pulls those masses in and that decreases its rotational inertia to like half the value. It just have a nice number to work with. 25 kilogram meter squared. Right. What would the final omega have to be? Okay. Well, if the I value doubled, do you see that the I value got cut in half? Do you see that the omega has to double to compensate for that? Right. So that I got 500 units of angular momentum on the left side. I better have 500 on the right side. And the only way to do that is for this to be 20 radians per second. So you guys see they speed up spinning. Like that. That's conservation of the angular momentum. Now, I did mention kinetic energy, thinking like, should we use that process? And then like, no, rejected that idea. But I do remember when we solved a bunch of collision problems, we did keep our eye on kinetic energy and watched it change, unless of course it was in elastic collision, and then kinetic energy stayed the same before and after the collision. But for all of the collisions, it went down. Okay? Or if you had the opposite type process, like a grenade exploding, or like Wanda throwing the ball on the magic school bus frictionless field, you got to take backwards, then kinetic energy would increase, but only because that energy was coming from somewhere. Like grenade exploding was a chemical reaction, or like throwing the baseball that would come from your muscles. Hey, I bet Paul Hewitt pulling those weights in, there was energy probably coming from his muscles and like adding kinetic energy to the system. Which of these frames, before or after, do you think there's more kinetic energy in the system? How many guys say before? How many guys say after? Yeah. You guys are saying this one, right? Let's check. Now, I just made up some random numbers, but I'll tell you what, I can pick any set of numbers, and you should always get the same result. Let's see if you guys are right. You guys remember at the tail end of yesterday, one of the last things I told you guys was rotational kinetic energy was 1/2 I omega squared. You guys see how that's analogous to 1/2 mv squared. Okay. So what was k naught, and what was k final? Well, I'm going to use these numbers exactly, just crazy made up numbers. Let's go 1/2 times I of 50 kilogram meter squared times the original omega of 10 radians per second. And don't forget to square that. Let's see. This comes out to, punches the calculator, 1/2, 50, 10 squared. I'm looking at 2,500. What's the unit that goes with that? 2,500 what? How do you measure energy? Joules. That's 2,500 joules. Good call. How about after he pulls these weights in? So 1/2 times, said half the rotational inertia, so 25 kilogram meter squared. But double the angular velocity, so up to 20. radians per second. Okay. Now, in the terms of the momentum conservation, the double and half balanced out, right? They had to, that was the whole point. How about the kinetic energy? Because, okay, so one value gets smaller, the other gets bigger. Is that also a wash? Well, no, because the angular velocity going up gets squared. So it's like the doubling counts twice. So this should be overall twice as much. Let's see if it is. 1/2 times 25 times 20 squared. 5,000 joules. Yep, that's exactly twice as much kinetic energy, twice the mechanical energy from before. Again, that energy didn't appear from nowhere. It came from his muscles doing some work on those weights to pull them in. Right? That makes sense? All right. There is an angular momentum associated with a single point mass. So let's look at that really fast. Here's just in general, L equals I times omega. Okay. But what would the angular momentum of a point mass be? Okay. Well, I know what the rotational inertia of a point mass is. It's just plain mr squared. We talked about that before, mr squared. Okay. And well, I'm going to do another substitution for omega. Do you guys remember what omega is in terms of v? But here, if I got this Roosevelt right here on this turntable, give it a spin. It has a speed v, but it also has a angular velocity omega. Okay. These two have the same omega but different v's. Okay. You guys remember it's related to their radial distance from the center. Okay. And omega is equal to v divided by r. You guys remember that? Okay. Or you might say v is equal to omega times r. You know, going back and forth depending on where you're going. Okay. So you guys see that one of the r's is going to cancel, and that's going to leave you with L of a point mass is equal to, I've got an M, I've got a V, and I've got an R, MVR. Okay. Which actually looks pretty close to just regular linear momentum, doesn't it? Regular linear momentum is just MV multiplied by R. Okay, so you get angular momentum of a point mass. Okay, so that's a nice formula, but what's the story that goes with that? Because otherwise it looks pretty abstract. How about this? You might have this like swivel stick. You got the stick, and it's got this pivot point right here. Here's a pivot point. Okay. And I'm going to throw a blob of clay at this. Some mass. Comes this clay, being thrown at some v, some velocity. Okay. It's going to collide inelastically, though. And it's going to set this thing into motion. Now, this stick is, of course, free to swivel about this pivot point. You could go like this. Maybe my question would be, like, after it collides and sticks, inelastic, that would be definitely something to do with momentum. It's a collision. How fast is that thing going to rotate about that point? Hey, like an angular type motion, rotational motion. Okay. And the way I do that is, well, it does depend where it hits that stick. Because if it hits right at the pivot point, it's not going to rotate it at all. Probably the further away it gets, the force of impact, there's like more torque. Okay. And this does tie to torque also. I'll show you guys that in a few minutes. So hang tight on that. Okay. So something to do with this radial distance. You guys remember, like on a door, why the doorknob is opposite the hinges? Maximize that R. Okay. So I'm going to take this expression, MVR, and say that is equal to the total rotational inertia of the clay plus stick system times how fast it's spinning. And then I can figure out the spin rate. So suppose this is on a horizontal plane, for example, and there's no friction after the collision. This thing's going to just start rotating, going round, 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 round. How fast? Whatever omega is. Now, what is I? I have to consider both these objects. What are their masses? What's this length? That whole thing. I'm not going to solve that with you guys, but just to show you guys that that's how that would work. Actually, I don't think your book even goes into quite that much detail, but that's there. That's how that works. That's a thought process for that. Yeah. All right. I bet a lot of you guys are probably waiting for this gyroscope. So that video you saw said, why is this stay up? Said, well, it's difficult to explain. It's something to do with angular momentum. So I'll try to give you guys a bit better explanation of that. I did want you guys to see the video because they did all kinds of really cool tricks that, well, I get sort of one shot with this thing because get one spin with this. Okay. I'm gonna, here, if I set this gyroscope up, okay, can I balance this thing? Well, it always falls over. Maybe you could balance it. It'd be really, really hard because there's a tiny, tiny, tiny base of support there. Tiny, tiny, tiny. Okay? In the center mass of this thing, whenever it leaves that base of support, there's going to be a torque. It's just going to fall over. Similar story with a coin. Can you balance a coin on its side? Maybe. Really hard to do. Maybe if you had a nickel, it'd be a little bit easier. It's a little bit wider, but really hard to do. Right? It's just going to fall over. Right? But if you set these things spinning, now that'll all stay up, at least for a few seconds. And similar story here. Here. All right. One shot with this thing. See if I can get this to work. Oh, oops, string got tangled, but hey, all right, it's working all right. Okay, so yeah, so actually I stayed upright for a while. So why is it that when it's spinning, it sort of like seems to defy gravity and it'll actually stay up? I think I played a clip for you guys a few weeks back when we did another piece of rotation. I said this was good, should come back. So today's the day from Vsauce, this YouTube channel. If you guys want to go back and watch this whole video, it's on YouTube. It's called Spinning. And I'm going to steal his explanation from like some point in the middle of the video, because he has a really good explanation for precession and why it would seem to defy gravity and stay up. So let's go to this is going to look like a weird story to explain this, but this will make sense in the end. Let's have a satellite orbiting a planet. So here's a planet, equator. Okay. And I'm going to have the satellite here in orbit around this planet. Say on this like dashed line, here's behind the planet, path, like this orbit. Okay. So it's going around, zoom, zoom, zoom. Okay. See it going around? Okay, so it's in a stable orbit, all good. It's got some mass, it's got some velocity, v. Okay, so it has some momentum at this point, doesn't it? It has some momentum, right? All fine and good. Now, what if I come along and I give it a downward force? I give it a little bump, like bump. So I'm going to apply a downward force just right there, just instantaneously, like bump. What would that do to the motion of that satellite? Well, it already has some rightward momentum, so it's going to keep going to the right. But it's also been knocked downward, so it's going to take a path kind of like this. But of course, the gravity of the planet is going to pull it back, so it's going to stay in orbit. And its new orbital shape is going to look more like this right here. Let's set up. Okay, that's not too bad. That type shape. Okay, so when I give it a bump down here, it's going to keep moving forward, but also then shift downwards. It's going to take this type path. And do you guys see that the maximum deviation from its original path is actually going to be 90 degrees ahead in the rotation from where the force was applied? I applied the force here. Its maximum displacement from its original path is like 90 degrees ahead in the rotation. You see that? Okay. Huh. Okay, so that's kind of interesting. What if I had not just one satellite, but what if I had like a whole like train of satellites, just like a whole conga line, like zoom, 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 right? And then every time they pass this point, I'll apply that force. It's like doink, 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 like a whole assembly line of these things. Okay. Wouldn't they all go from this original path to this new shifted path, something like that? In fact, you know, what if it wasn't like a billion different independent satellites, but what if it was just like a solid ring of satellites? And they applied the force here, like doink, doink, doink. Okay? Wouldn't that just shift the whole ring like 90 degrees ahead in its rotation? Hey, kind of like this gyroscope, right? This, like any individual point, like particle, it might represent like the satellite, right? Something like that. And if this thing is starting to like fall over because, say its center mass is not above this tiny, tiny base of support, there's going to be a torque that makes it want to fall over this way, right? And it would fall over that way if it's not spinning. But if it's spinning, remember, it actually falls like 90 degrees ahead of that force point, of that torque. And that will make it precess. That's why in that video you saw, it looked like it was like levitating, like defying gravity, but it was always like making this like precession type movement. Guess that? Motion. Right? So that is how a gyroscope would stay up. All right. Now, I did a minute ago say that this was tied to torque when I was talking about like the swivel stick and this angular momentum of a point. So let's tie this to torque. How is torque related to angular momentum? And for that, let's go back to a model that I solved solved a problem with you guys yesterday of like a solid disk. Hey, kind of like this. This is like a solid rotating disk, pretty much, right? Pretty close to. Maybe it has some mass. Maybe it has a radial size r, and I'm going to wind a string around it. It's like zoom, 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 and then pull with some force right here, where as I pull the string with a constant force, is that going to cause this to speed up spinning? It's going to rotate about this axis, some omega. Which is changing. It's going to be variable. As I apply the force, it's going to spin faster, faster, faster. Okay. But this force and this radial distance will always be at right angles to each other, right? Because just for the shape of how that works. Here's the axis of rotation right here. Okay. Rotation. Okay. So where we went with the story yesterday was that the torque that you apply is r cross f, but it's just the magnitude of r times the magnitude of the f because they're at right angles. So I should say times time of 90 degrees, but that's just one. And we said that's also equal to I times alpha, because torque equals I alpha. That's analogous to F equals ma, torque equals I alpha. And then we went and solved for alpha. Now, that's not where I'm going with the story today, but I just want to remind you guys what we did yesterday. Okay. Let's set up a couple of graphs. And this is actually going to be the last new poster that's hanging up on my ceiling. I think I've covered all of them except for this one that we're doing right now. This will be the last step we have to do. Actually, I'm going to reverse these how they're printed on the poster too. So I'm going to do torque in Newton meters as a function of time and seconds. And then this one, I'm going to do angular momentum in kilogram meters squared per second as a function of time and seconds. Okay. Now I'll tell you guys what else too, and this is going to help us out a bit, is that at this point in the class, we're definitely getting some pretty complex composite units, I mean kilogram meters squared per second. So sometimes there's multiple ways to express these things. In terms of newtons, here's what this is also equivalent to. Newton times meters times seconds. It's the same thing. I'll show you guys why. Newton is the same thing as kilogram meter per second squared. You know that one is F equals ma, Newton's equivalent. So kilogram meter per second squared times meters times seconds, that is the same thing as kilogram meter squared per second. That's the same thing as this one right here. Same thing. Right? Okay, so these graphs, I'm gonna draw some graphs. Actually, I want to see if you guys can beat me to the graphs. We're gonna start with this one on the left. Torque is a function of time. So let's have 3 seconds ticking. Tick, tick, tick. So time's ticking along. Right? And let's suppose I'm pulling with a constant force. I'm just pulling the string with a constant force, which of course making this thing speed up, but constant force for 3 seconds. Can you guys draw what the torque versus time graph would look like for a constant force at a constant radial distance for 3 seconds? What's that graph look like? Right here. Constant force for a constant radial. Hey, if it's a constant force for a constant radial distance, isn't that a constant torque? Did you guys just draw that right there? Flat line, constant torque? Yeah, whatever this torque is. Guys get that? Okay. And the fact that that constant torque is making the speed up faster, 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 which you definitely, you know that from yesterday because there was an alpha value. The fact that there's alpha, angular acceleration has to be speeding up spinning. Isn't this also acquiring more and more angular momentum, right? Hey, kind of like this gyroscope has some angular momentum. In fact, this picture kind of looks like this gyroscope, doesn't it? It kind of looks like it. Like more and more angular momentum. So what is this graph on the right doing? Let's suppose it starts from rest. I'll give you guys at least this point. Can you guys draw the rest of the graph on the right? Tick, 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 tick. Did you guys draw this? Is that what you guys just drew? Just like that? Okay. Okay, now these two graphs are related to each other. Right. How are they related to each other? Okay. Well, one thing that you can get from this class is and you guys have seen lots of different kinds of graphs, lots of different information is embedded in the graphs. What are these relationships? Okay. Take a look at the units of the axes, because there's a big hint right there. Okay. I've got on this torque versus time, Newton meters as the height and seconds as the width. Okay. So, I wonder if maybe does the area under the curve represent something possibly? Okay. Has a height in Newton meters, has a base in seconds. That'd be an area that represents some number of Newton meter seconds, right? Hey, that's what this is, Newton meter seconds. Okay. So the area under torque versus time tells you like the acquired angular momentum, like the change in angular momentum. Okay. So I'll call this area delta L, right? Change in angular momentum. Okay. And see how during the first second it picks up like this rectangle shape, and the next second it picks up the equal rectangle, and the third second picks up another rectangle, and they're equal sized rectangles. That means that this angular momentum is picking up at a constant rate. That's why this line is specifically a straight line, like a linear relationship. And on this graph, the delta L is, of course, the change in height of that graph, delta L. Okay, so change in height of this graph and the area of this graph, same thing. Is that? Here's, I'm running out of space on this paper, but right, one more thing here. This delta L is the same thing as a torque applied for some time interval. Okay, same thing. Okay. And you know what that looks like? One more thing, one part of this graph. What's the slope of this graph equal to? The slope of this graph? The torque. Okay, so it's the torque. Okay. Right, so the expression I just wrote, the acquired angular momentum is torque times time interval. Hey, does that look like impulse from change in momentum is force times time interval? That sure does look like that, doesn't it? Okay. So back in the day, actually just a couple weeks back, you guys remember how impulse delta P was, it was mass times change in velocity, but that came from applying a force for some time interval. Okay. Well, we've got a rotational equivalent to that, and that's change in angular momentum, say like angular impulse, is I times change in omega for a constant I. Now you wouldn't need a constant I for that, like a rigid object. And that comes from applying a torque for time interval. That's what we just did graphically, something like that. Okay. Okay, now, side note on this, if you had a changing I value, which you did say for the Paul Hewitt situation, then, well, this would work out a little bit differently. Great. But also the Paul Hewitt situation on the rotating platform, there would be no change in angular momentum at all because this was conserved. That's how we solved that problem. But that was because that was a closed system. And this right here would be an open system, right? This term to because there's an outside force acting on the whole thing. Okay, is that? Okay, is it? And that sums up the list of the course things that I wanted to tell you guys about to kickstart this rotational dynamics. So 2 more things for the end of class. One is that tomorrow, have you guys build an O'Neill cylinder? So let's go back and review the physics of that. So you guys remember what O'Neill cylinder is? It's a giant cylinder spinning in space to produce like some artificial gravity. Okay. So got this giant ring, deep space. There's no real gravity around. It's just a deep space. Like you would be like floating around like an astronaut. I'm gonna draw a ladder going across this just for visual context. Won't do anything with the ladder today, but maybe in the future. Okay. Right. And let's say you know what the size of this O'Neill cylinder is. So I'm going to make up a number. Let's say diameter is 10 kilometers. Okay. And I want to know how fast do you have to get this thing spinning, omega, solve for omega, so that all these people walking around on the inside, and they would feel like they could walk around like they were right side up if this thing is spinning, okay, feel like there's an artificial gravity, G artificial, of 10 meters per second squared. Like they were on Earth. So this thing's spinning, zoom, zoom, zoom. Now, if these people are blindfolded, they might even think they're on Earth, and it might be kind of hard to tell the difference that they're not. Well, maybe until they start climbing this ladder. But so 2 questions. First question is, what is omega? How fast things spinning in radians per second? O'Neill cylinder specifically this big, so that you achieve this artificial gravity. And the follow-up question is going to be, what's the time period? So what is omega in radians per second? And what is the time period in, I don't know, maybe like seconds for this O'Neill cylinder? Hence, centripetal force could be called mv squared over r, or centripetal force might be called m omega squared times r. Sometimes one of those is more convenient than the other, depending on what kind of problem you're working with. I'm going to give you guys a 30-second head start to beat me to the answer. How fast is that spinning? And furthermore, how much time would it take to rotate once? 10-kilometer diameter. Do anybody happen to solve it by now? And I know it's kind of fast, but here, let you guys see this. So I did give you guys enough information to solve this, but you do have to manipulate some of these numbers because, I mean, you don't really care about diameter so much as radius for these formulas, right? So maybe like 5,000 meter radius. That's another detail. You don't want kilometers, you want meters. So do you guys see a 5,000 meter radius? Also, this target gravity, 10 meters per second squared, that's really an acceleration value, isn't it? Not really a force. So do you guys remember how to get to acceleration from force? You just divide by the mass. That's Newton's second law of motion. So let's do this. Centripetal acceleration is just plain omega squared times r. I'm definitely using this bottom one because we're solving for omega. Right? I said. I see how this is going to come together because the target acceleration is 10 meters per second squared. Solving for omega. And the radial size is 5,000 meters. Is that? Yeah. So 2 steps to get to the answer. Going to divide by 5,000 and then take the square root. So omega is 10 meters per second squared. Divide by 5,000 meters. Square root. Let's see what that is. Square root 10 on 5,000. That's 0.0447 radians per second. If you're curious, times 180 over pi, that's the same thing as 2.56 degrees per second. So if you have a protractor, you can say count 2.5 degrees, say rotate that much every second. So you can watch this thing spinning, and you can see it spin about 2 or 3 degrees per second. You can watch it rotate real slow. The other question though was how much time does it rotate once? Now, I'm going to solve that with the dimensional analysis table. So time period equals, I want 2 pi revolution, or 2 pi radians, 1 revolution, 2 pi radians. You could have even said 360 degrees and played off this other number. 0.0447 radians per second, or 2.56 degrees per second if you went with 360 degrees. Let's see what that lands us. So what's 2 pi radians divided by 0.0447 radians per second? Okay, I'm getting 141 seconds. Keep in mind, this only worked out because I was working in radians. This whole square root stuff, naturally gave me radians. That's everything. 141 seconds. If you like, you could do this 60 seconds per minute. Divided by 60. Okay. I'm looking at 2.34 minutes. So that's 2 minutes. Subtract 2, multiply the 60 back in, and 21 seconds. 2 minutes. Okay, so in the future, when we have O'Neill cylinders, and the only reason we don't right now is because it's really expensive to get stuff into space. But someday, say you had one that was 10 kilometers in diameter, you would want this to rotate once, exactly every 2 minutes, 21 seconds, so that the people on the inside feel like they're on Earth gravity. Guys get that? All right, last thing. I've got an engineering question for you guys. Suppose you guys are driving a car and you guys leave the interstate at 70 miles an hour. You guys go into a tight turn on the off ramp. and you realize, oh man, feels like this car is about to flip. Okay. The car's gonna flip if its center of gravity ever leaves the base of support. Now you guys know that here, drawing a couple. You guys will see why I'm drawing two cars here in a minute. There's gonna be a front and a back. Right, front and a back. Right. You have four wheels, which gives you a rectangle base of support. Right, rectangle base of support. Okay. Now, part of this is the fact that the car is three-dimensional. You guys know if you step on the brake, it's going to rotate forward a little bit, turn the side a little bit, right? So I'm going to give you sort of a simplified model, but that is part of this, is the fact that the car is three-dimensional. Okay? So what if you as an engineer are tasked to come up with a three-wheel car? You've got two options. You can either put one wheel on the front and two on the back, or two on the front and one on the back. And it turns out that one of these is much safer than the other. Okay, so here's a triangle base of support now, right? Okay. Guys, you guys sorted through this. Quick show of hands. How many guys think that it's safer to put one wheel on the front? Who thinks that? Who thinks that? Who thinks it's safer to have the one wheel on the back? Okay, so a few votes on each one. You guys got to see. There's a famous example of this. All right, so we're running a little short on time, so take us through this a little bit faster than I need to. But suppose that you guys see an air freshener hanging on your rearview mirror. If you slam on the gas pedal, does it move back a little bit? If you slam on the brake, does it go swing forward? What is a greater magnitude of acceleration? Speeding up, like, or slamming on the brake? What's more acceleration? Slamming the brake. Okay. So I bet it can swing forward a lot more than it can swing backward. Okay. And if you turn left, everything seems to go to the right. Now there's a whole story of that. It's just relative. It's not really going to the right. It's just inertia relative to the car. Okay. And then right, same thing, right? So far, just hitting the gas pedal, the brake, looks like the center of gravity stayed over the base of support. But if you throw in some steering wheel action on top of speeding up or braking, do you guys see which one of these the center of gravity sort of like left the base of support and the car's going to topple over? Which one did that just happen? How about this scenario right here? So one wheel in front, if you brake and say turn to the right or to the left, okay, so braking and turning is the dangerous situation for one wheel in the front. Okay. Let's switch over and watch Reliant Robin. Oh yeah.